All right. Thank you, Nima, for the introduction. So what I'd like to do today is take this opportunity and talk about some of the work that is being done in the area of in-memory computing, in particular, actually, for machine learning accelerators. And I'll look at basically different kinds of opportunities or challenges that we have today. Now, certainly, deep learning is achieving milestones every day, right? I mean, you open up a tech journal, it doesn't matter, in any newspaper these days, you find that deep learning is in the news all the time. Be it an impressive advance in hyperbolic coverage, or for example, Waymo opens up driverless robotaxi service to Phoenix, to the public in Phoenix, and so on. Now, certainly, if I were to really look at the deep learning saga, back in 1997. Deep Blue beat Kasparov, and then in 2011, Watson wins Jeopardy. But more importantly, back in 2016 and onwards, the advent of deep learning has which has been fueled by powerful GPUs and so on. What we found is that today it's very, very difficult to beat the machines in a lot of these games. AlphaGo beating Lee Sedol, and certainly. In case of autonomous driving and all, certainly deep learning has been used. But the question, of course, is at what cost? And if you're to really look at the power consumption in some of these, very high performance machines and so on, they are of the order of about 200 to 300,000 watts. However, sort of brain in a lot of ways does these things that possibly, and again, with a question mark, about 20 watts or so. And so certainly the trend today is algorithms moving closer and closer to hopefully what the brain does. But certainly the hardware cost is moving further and further. So the aspirations have grown faster than the technology available to satisfy them. So let's look at the compute demands. And that's a big problem. And if I were to really look at training, and this is an example where I'm showing, if you look at NAS, which is the network architecture synthesis, the number of operations required for doing NAS on transformer is about 10 to the 21 zeta operations. And correspondingly, if I were to really look at the CO2 emission from NAS, it's about 315x higher than air travel from New York to San Francisco per passenger. Now, that's not it. If we are to really look at, for example, edge applications and edge intelligence, and we did a case study on object recognition and smart glass with state-of-the-art accelerator, in this particular case, a Google Edge TPU, and we did an analysis of implementing a RetinaNet DNN, which is for object detection, on smart glass. And what we found is that under ideal conditions, the time to die for the battery is about 1 hour, and that's under ideal conditions. If you really look at all the non-idealities and other things that we'll be implementing on that smart glass, it's probably going to be less than half an hour or so. So the question, of course, is where do these inefficiencies come from? We certainly have an existential proof that the brain is reasonably efficient. So to that effect, inefficiencies probably come from not knowing the right kind of algorithms, not having the right kind of hardware architectures, and not certainly having the neurons and synapses in the form of the circuits that we use today. So what I'm going to be focusing on today is mostly on the hardware architecture and the circuits part of it, and to a certain extent the devices, and try to address this problem and see what are the possibilities and challenges exist today. So if I were to really look at AI hardware from the circuits architecture and the devices primitives, turns out that the circuit and architecture can, what we would like to have is the architecture and the circuits to, embody the computing principles of the brain and to be able to do these computations separately. Turns out, and if I were to be able to do the computations very near the memory or in the memory itself, as possibly what is done in the brain, we can potentially get a large amount of improvement. And that's sort of in line with what we actually observe in the computer architecture community, where there is a, what's called the von Neumann bottleneck. If you were to really get stuff from the memory and access the memory, get the values out, take it to the CPU, do the computations and bring it back to the memory, that traffic is large and that is very, very inefficient. So to that effect, is it possible that I am able to do, near or in-memory computing or the computation in the memory itself with the right kind of devices and the interconnects? So where are we today? Today, certainly, if you look at the multi-cores and GPUs, they are certainly not doing in-memory computing, or they try to certainly do near memory computing in some of these cases. There are several architectures and accelerators which are being built to do these computations which are fast and efficient. But what we really feel is that there's a need to really think about hardware which is specific to some of these machine learning applications, and in particular take advantage of the fact that, hey, some of these devices can potentially be effectively used for computing memory. And to that effect, and again, as I mentioned, I'm going to be focusing on near and in-memory computing and neuromorphic devices and potential interconnects to counter that effect. So what is in-memory computing? Now, if I were to really look at, and again, probably I'm preaching to the choir, there have been several talks on in-memory computing, but for the sake of completeness, what I'm going to do is I'm going to talk about the basics of in-memory computing. So if I were to really look at a standard memory with peripherals that we, in general, turn on one word line at a time, and the peripherals are really the sense amplifiers. So now it turns out that if you're able to, in some ways, be able to turn on multiple word lines, in this particular case, I'm showing 2 word lines, one can show under certain circumstances and making some modifications to the memory, you will actually be able to do, for example, bitwise AND operations, NOR operations, or Boolean operations. Now, what you can do further, of course, that would require a little bit of change in the, the peripheral circuitry. Now, with a bit more change in the peripheral circuitry and with some more changes in the array, it turns out if you're able to turn on multiple word lines simultaneously, you will actually be able to do some matrix vector multiplication operations. And that turns out, as we'll see, is very important for all these machine learning applications that we can be talking about. Now, the question, of course, is that, what kind of memory technology should I use? There's been a lot of effort these days on coming up with the new non-volatile memory technologies. And we'll certainly talk about that, the RRAMs, PCMs, and STT MRAMs, and so on. But it turns out it's also possible to do some of these in-memory computing using SRAM, albeit you have to pay a lot more in terms of area for doing some of these computations. However, SRAM certainly has certain kinds of advantages, as we'll see. Finally, what I'll also do is I'll talk a little bit about doing compute in memory, but in a little bit different way, using ROMs, meaning thereby if it's possible to embed a ROM into a RAM, and I'll talk about that later on, at no extra cost, it turns out you might actually be able to do some of these transcendental functions in your ROM at no extra cost and be able to actually do these computations without having possibly a map table to load from the main memory to your caches and so on. So with that in mind, let me just focus now on in-memory computing, and in particular, actually analog in-memory computing, as we'll see. Again, as I mentioned earlier, deep learning needs a lot of matrix vector multiplication units, and this is actually a slide borrowed from IBM, which shows that for speech, language, vision applications, and so on, the red bars which are shown there, which are basically matrix multiplication, those are the major operations that we need to do. And if you're able to effectively do that at low cost, low energy consumption, then there's a possibility of getting a good amount of improvement in some of these machine learning applications. Now, what kind of non-volatile memory technologies one can potentially use, and I'm going to be focusing on some of these in a little more detail. I'm showing a bunch of these colorful devices here. And we're not going to go into details of some of these really colorful devices going all the way from lateral spin valves to magnetic tunnel junctions to RRAMs, PCMs, and in fact even skyrmions. They can all potentially be neuromimetic devices. But again, as I said, I'm not going to be focusing on that. I'm mostly going to be focusing on CMOS. Along with that, I'm going to also talk about RRAMs, PCMs, those are, and STT MRAMs, those are a little more mature technology. So if I were to really look at the fundamental building blocks of in-memory computing, and then the basic idea, let's look at it, is that I'm going to potentially think of a crossbar where I have these devices which are shown there on the right here, with these devices with some access transistors. And these, if I were to really go into a little bit more details of these, this crossbar array, if I were to apply a voltage V on the left, then what I'm going to get on the at the bottom, considering the fact that each of those devices have a conductance which is given by G, I'm going to get a summation of VI GI from Kirchhoff's law, and that's basically the current that I'm going to get, and an analog value of the current. Now, if I were to really look at some of these devices, as I mentioned, as in the previous slide, they could potentially be a PCM, could potentially be an RRAM, STTM RAM, SOTM RAMs, or it can even be, for example, a CMOS, set of CMOS transistors implementing some of these functions, like a 60 cell or an 80 cell. Now, a few things which are also required. Turns out, since I'm doing analog computation, analog, certainly putting everything in the analog domain, and when these crossbar arrays have to communicate with other crossbar arrays, there's a need to really think about not doing that communication in the analog domain, because the analog noise then is going to get added up and might have more of a problem in terms of having the right kind of accuracy for your system. That can degrade considerably due to analog noise. And it's difficult to learn analog noise. So to that effect, what you really need is some peripherals. And these peripherals could potentially include, for example, first of all, since I'm getting a current at the output, you need some sort of a converter from current to voltage, depending on the kind of devices that you end up using. And then finally, an analog to digital converter. And as we'll see later on, that these analog to digital converters can certainly be a bottleneck when you do such a design. And certainly there are, there's a whole bunch of work which is going on and coming up with the right kind of selector devices to take up less area. And but I'm going to assume that most of the cases that selected device is going to be a transistor. Now, what one can now do is take all these, crossbar arrays and put them together along with their analog to digital converters, which are potentially can think of as basically neurons. And you can connect them in a spatially distributed set of cores, which are connected in the form of a network on a chip. And if I were to now take that basic idea, which I showed in the previous slide, having these cores doing basically this, a matrix vector multiplication operation, and then I have a bunch of those cores, which are shown as core 0, core 1 in a tile, and each of those tiles are going to have some shared memory, some, again, logic to do some other computations, accumulating the results and so on. And so one can potentially think of a network on a chip architecture, which are a bunch of these tiles consisting of each of those cores connected in a network on a chip. It's a massively parallel accelerator, certainly amenable to data level parallelism, and could potentially be quite efficient for machine learning applications. And again, a spatial architecture is what I'm going to be considering first. And so the idea is that if we have your memories, which are small enough, you can fit everything into this architecture. Now, this is an architecture Puma that we worked with along with HP to develop, and a simulator for cycle accurate simulator is available in the GitHub. So if I were to now go into a little more details of that architecture, and I'm not going to spend a whole lot of time on it, the idea is that features this kind of architectures can analyze memory compute characteristics for ML applications. It's an ISA programmable accelerator with hybrid CMOS and NVM technology, a non-volatile technology, and it doesn't have to be NVM. It could also be CMOS, but CMOS would end up taking a lot more area. So a Puma core, as I mentioned, certainly consists of these matrix vector multiplication unit, and also doing some vector operations. And then the Puma tile is, you can have multiple of these cores in a particular tile. And these tiles, again, are put together into a data flow architecture. And finally, you have a Puma compiler, compiled to the Puma ISA. And you can use any one of those machine learning frameworks like TensorFlow, PyTorch, and others. Now, few things which are quite important, and I'm going to switch gear a little bit and focus really now on the crossbar part of it. How about the weights and the inputs? As I mentioned earlier, one can potentially think of each of those crossbar devices to be an analog memory device. They can store 1 bit, 2 bits, or multiple bits at a time. In general, that's more difficult to do, having multiple bits because you have to have a complex analog to digital converters. So one can potentially think of having 1 or 2 bits per each of those devices. One can certainly have more, but then you may not be able to turn on a good number of these rows simultaneously. Now, each of those devices one can potentially think of as, let's say that I'm doing 4-bit computations, 4-bit weights. They can be, and let's say that each device has 2-bit weights, let's say, as an example, then I need 2 crossbars. So I'm basically end up doing some sort of weight slicing. On the other side of it, in order to actually have the least amount of analog noise, one can also do what's called bit streaming. Let's say that if I have an input of 5, then you can actually stream the bits as 101, and then finally you have to accumulate the results. And so to that effect, bit slicing, which includes weight slicing and input streaming, would enable low precision crossbars and low precision DACs, the digital to analog converters that are required to compose high precision matrix vector multiplication units. Now let's look at a little more into the cores that I talked about earlier, the PUMA cores. These are the heterogeneous cores, and one can potentially think of doing, as an example, let's say that I'm doing multi-layer perceptrons. So we have these inputs which are coming in, and then you do this matrix vector multiplication, z is equal to mx, and then followed by, let's say, you have a neuron which is doing the sigmoid operation. And so what would one have to do in that case is you have to load, do the MVM operations in the crossbar, then you have the ALU to do basically my sigmoid operation, and you store the value. Now, a few things which are also important, as I mentioned earlier, that when you look at these crossbars, the size of the crossbar turns out to be important. You may not be able to implement because of various constraints and non-idealities and the complexity of the A to D converters and all. You may not be able to use a 2000 by a 2000 crossbar, right? Or 2048 by 2048 crossbar. So your crossbars are going to be smaller. So to that effect, there's a need for really thinking about these MLP operations that I talked about that maps on multiple matrix vector multiplication units, and you have to accumulate the results. So what then one has to think about is that for all the partial sums, you have to bring all the partial sums from the different cores and accumulate the partial results, right? And so larger matrices would require more data movements to compute the effective matrix vector multiplication units. Now, so the wish list that you'd like to have from the device side, and again, is the fact that my device has to have, if I could have multi-level cells, that it's ideal, right? High endurance. Device linearity turns out to be important when I end up writing into the cells, and reasonably high on to off ratio of these devices, because otherwise your source resistance and the sink resistance are going to come into picture, and that can mess up things a little bit. Now, from the macro level, you certainly would like to have a reasonable size crossbar. You don't want your crossbars to be of the size of 4x4 or so on. So you'd like a larger crossbar, but you're limited by also certain factors, as I mentioned earlier, the non-idealities, the complexity of the A to D converters, and so on. You'd like to have low peripheral overhead, good selected device. I didn't talk much about it. Source to sink resistance, I briefly talked about it, and the line resistance. And finally, from the architecture side of things, what you'd like to have in a spatial architecture like what I just mentioned, you'd like to have the minimal amount of data movement. You'd like to do effective MVMs, vector operations on these, either the non-volatile memory technologies or other CMOS technologies. And then finally, you need to be able to effectively, train, map it on this architecture and take advantage of sparsity. So just to go into a little more details on these NVM devices and the challenges one can face, as I mentioned, compared to CMOS, there are certain advantages: non-volatility, high density, low leakage. One can also show that leakage can certainly interestingly play an interesting role in sparsity, but I'm not going to go into the details of it. But current devices are highly nonlinear. Expensive write operations in most of these devices because of non-volatility, write power consumption goes up. And your R on to R off in a lot of devices are limited to about 10x. In some of these devices, it can even be lower. If I were to really talk about RRAMs, they have poor endurance, and RRAMs and PCRAMs. And it's certainly very difficult to do 4 bits per cell. So from the macro level, the challenges, as I mentioned earlier, the NVM crossbars can have various non-idealities. They include parasitics, non-ideal devices, line resistance, and so on. And such non-idealities can introduce varying amounts of functional errors. And the errors would increase as we increase the crossbar size. So to that effect, I'm basically showing the errors in a crossbar that we actually looked at. I'm plotting basically the I'm plotting the ideal current versus the non-ideal current from the crossbar. And as you can see that it should be 45-degree line under ideal conditions, but there's a good amount of variability. And now if I really bring in larger crossbars, there's non-ideality factor increases, and one has to take care of it in terms of training and other issues. Few things, as I mentioned earlier, the crossbars have to communicate with each other in terms of the ADCs and the DACs. And we'll see that depending on the kind of the size of the crossbar that you use and the ADCs end up dominating the total area and the energy consumption. So that becomes a really an important issue when you design such crossbars. Finally, how about modeling these crossbars? It turns out it's quite important to model these crossbars. And when we looked at these crossbars earlier, remember I wrote it as, the current that I get is summation of VI times GI, right? And that's sort of a linear operation that we can do. But in reality, if I were to really think about devices to be nonlinear, which you can have these devices and you'll have the access transistors, again, will have nonlinearities. These access devices, it turns out the column current that I was talking about earlier, it's not summation of VI times GI, it cannot be very easily written that way, but it's really a function of VI and GI. And in this particular case, the GI is also going to be a function of V, which is the voltage. Also source resistance, sink resistance, and so on. So now modeling these crossbars, if you were to simulate, that becomes quite important because there's non-idealities is going to play a very important role. So you may not be able to write it as simple summation of VI times GI. So to that effect, there's a need for modeling these crossbars effectively, where F is a data-dependent nonlinear function. Now it turns out, one can try to model it effectively, and one can use SPICE to do that, but that's going to take you a long time to do. So to that effect, actually, we used neural networks to model these crossbars for capturing the interdependence of its inputs. And there's several issues that are required in order to model these kind of computations in crossbars using a neural network. I'm not going to the details of it. It was actually published in DAC of 2020, that was last year. And what it really tells you is that it's possible to actually use this kind of modeling technique, GenieX, which is a generalized approach to emulating non-ideality in memory-centric crossbars, provides a modeling capability for different kinds of non-idealities. The training of it is done using either, for example, fabricated crossbars or using SPICE simulations as the input data. Now, from the architectural level, the challenges, as I mentioned, in a spatial architecture like that, you might have to send data from, within across cores, which are within a tile, but sometimes across cores, right? So the data movement between MVMUs, which includes partial sums, activations, is frequent. And to that effect, what I'm showing here is that the intertile, intercore, and intracore communication costs do have to be considered. And of course, when you map it, intertile certainly dominates all the communication cost. Few other things which are also important is that the matrix vector multiplication alone cannot execute all the ML applications. So you have to look at all kinds of other applications which have to be included in your tiles and the cores. This is basically the a resistive crossbar-based accelerator design flow one can potentially think of. On the left side, what I'm showing is that IMC-aware workload adaptation. IMC is in-memory computing-aware workload adaptation. That can include, for example, crossbar-aware pruning, crossbar-aware quantization. I'm not talking about these. Crossbar-aware training algorithms, and again, I'll briefly talk about that later on, and crossbar-aware mapping algorithms. The IMC, workload, IMC-aware workloads that one should look at, different kinds of based on different kinds of architectural specifications. And on the extreme right, what I'm really showing is basically the different kinds of device and circuit level models that one has to look at. And that includes PCMs, RMs, magnetic tunnel junctions, or in fact, even the CMOS technology. RTL design synthesis, one can use cacti and other kinds of tools to actually model that, the memories and the interconnects. And finally, in the middle, the core of it is IMC-aware workload evaluation, which, as I mentioned earlier, for a Puma-like architecture, one can use the compilations, and then, of course, cycle level simulation, iterative MVMs, the matrix vector multiplication, tiling, bit slicing. Remember I talked about, and those are the simulations that does. So this entire workflow certainly is available to actually evaluate the effectiveness of the computing memory technologies. Just wanted to actually show you some results of using the PCM, using this kind of an architecture and the tools that have been developed. We looked at multi-level perceptrons, deep neural networks, wide neural networks that includes LSTMs and RNNs, and of course, convolutional neural networks. And again, the inference energy is what I'm talking about here, shows that it's certainly possible to get more than 100x improvement in energy consumption. In some cases, certainly more than that, using a batch size of 1 in this particular case, compared to Skylake, Pascal, and Pascal. A few other things, as I mentioned earlier, that in this in-memory computing architecture, you're really dominated by the matrix vector multiplication costs. So the idea is to really see if it's possible to reduce the matrix vector multiplication cost in some ways. There are different ways one can do that. Later on, I'll talk about ADCs, which are programmable ADCs. And so that, depending on the sparsity that you have in your matrix, you might actually be able to use, if you need a 7-bit ADC, you might actually be able to use a 5-bit instead and get improvement in energy consumption. So you need to potentially think of a programmable ADC. Now, of course, the next question that comes is that, is it possible at all to get rid of the ADC completely? So to that effect, one can first think of, ADC-less design. Now, of course, it may be difficult to do for very complex designs to have completely, ADC-less design, but certainly, if you're starting with, for edge applications, if you're able to use a single-bit ADC, which is basically boils down to be a sense amplifier, then of course you can reduce the energy cost considerably for edge kind of applications. So area and energy profile, as I mentioned, dominated by ADCs and SIM accelerators, the computing memory accelerators. I'm using the word SIM and in-memory computing interchangeably, but they really mean the same. So this is actually a work that was going to be presented at DATE this year, which is basically showing, hey, is it possible that I actually take an array and really replace all my ADCs with just a 1-bit ADC or a sense amplifier? And if I'm able to do that, then of course I have an improvement in energy consumption, and the area also improves drastically quite a bit. But how do I do that? If I do. So it turns out we have to actually now use training. So software or training co-design with this ADCs is what you have to do. So ADC-less SIM accelerators have 1-bit partial sums, and so there's a need for partial sum quantization aware training. Now again, remember that it's possible to actually train on the quantization, but difficult to actually train on the analog noise. But again, one can train on these quantizations and trainable quantization functions to get high accuracy. So at the end of it, if I have to really think about the forward pass, the forward pass is used something like what's shown on the right. So like a sigmoid kind of function. It's basically minus A or plus A. And then, you approximate it in your backward pass so that it's actually, trainable or differentiable. So to that effect, actually, we did that. Each of those sense amplifiers training basically, and the forward passes are basically shown using these step function or these approximations for the backward pass. And if you do this kind of training, and we did that for CFAR 10 using ResNet 20, the results are actually kind of interesting. In all these cases, the SIM accelerators are 1-bit partial sums. And what I'd like to focus on is that, if I'm able to use 4-bit weights and 4-bit, inputs, and again, remember that it's used completely, 1-bit ADCs or the sense amplifiers, it's possible to get almost about 88% accuracy in case of array size of 32 or so. So it's possible to. Certainly, if you go to the ImageNet domain, you might actually need to have not just 1-bit ADCs, but maybe 2 or 3-bit ADCs. Now, let me switch gear a little bit, considering the time that I have. So far, I've talked about mostly RRAMs and PCMs kind of technologies, and as you know, that RRAMs and PCMs certainly are very good in terms of area, as you can see on the right. The cell area is 16F squared for PCMs and RRAMs. The MTJs, on the other hand, are probably a little bit larger, depending on if it's an SOT MTJ or just a standard magnetic tunnel junction, plain vanilla. Or the CMOS certainly would require quite a bit larger area. For the 60 cells, about 160 or 150 F squared, and the 80 cells are going to be about 30% larger. So, write energy, good amount of difference. CMOS certainly is way better and faster. And similarly, but more importantly, if you were to really think about endurance, 10 to the 7 cycles versus for the PCMs and the RRAMs to about MTJs having 10 to the 50, quite a bit larger, closer to basically the standard CMOS cells. So of course, for most of these architectures that we're talking about, using PCMs and RRAMs are mostly for inference, not so much for training. Whereas the CMOS and MTJs can potentially be also used for training, but each has its own kind of issues, as we'll see. So now let's look at CMOS as the technology of choice. And there's a need for really thinking about, again, very similar to what we've talked about earlier, simultaneously activating the word lines, and then modifying the memory peripherals for sensing. So let's look at a standard SRAM. So can I do in-memory bitwise Boolean operations by turning on 2 word lines simultaneously? Now, if you turn on 2 word lines simultaneously, there can be a short from VDD to ground. So that's not a good idea. So in such a cell, 60 cell, what one can show is, and one has shown, it turns out you can actually staggered activation of word lines. You activate word line 1 followed by word line 2, as I'm showing there. It's possible to staggeredly activate the word lines, and by staggered activation of these word lines, and having asymmetric sense amplifiers, it's possible to have at the output of it in the sense amplifiers really bitwise operations like NAND, NORs, and so on. Now, going a little bit further, and if you want to activate the word line simultaneously, then one can also use, for example, 80 cells. The difference between the 80 cells and the 60 cells is that the 60 in this particular case, which is shown here, and let me see if I can, okay. The 60 that I'm showing here is basically the for write operations, and on the right, what I'm showing is M1 and M2, which are basically the read transistors. And the read doesn't get affected by the read it's not a non-destructive read, because the Q or the Q bar of the cell is connected to M1, the gate of the M1. So the read part of the circuitry is shown here, which is with transistors M1 and M2, and there's a read word line. Now, if I activate 2 read word lines simultaneously, it turns out then I can again do Boolean operations. So this is an effective circuit showing that I'm turning on two word lines simultaneously, and I'm only showing basically the read part of the circuitry, M1 and M2. And it turns out if both are zeros, and if I pre-charge the bit line high, the output is going to be high. But if I do pre-charge the bit lines high, and if I have the inputs to be either 1, 1, 1, 0, or 0, 1, then of course the output will start discharging. And the amount of discharge is going to depend, how much of it discharges depends on what the inputs are. But if I have to plot it, 0, 0 is going to have still have output of VDD, and any one of these other ones is going to be 0 or closer to 0, depending on when the sense amplifier turns on. Now, if I put the threshold of the sense amplifier to be somewhere here, now I can do NOR operations. And by having a little more of complicated circuitry out there in the output, I can do NORs or NANDs, or in fact, even XOR operations. So if I'm able to do these XOR operations, then again, putting in a little bit of extra circuitry in my 8T cell, which I'm showing here, in my, making it a little more complex, I can actually do, and add operations and so on. And again, once I'm able to do add, I can also do multiply operations, not quite in the memory itself, but slightly outside the memory. And if I'm able to do these bitwise XOR operations or AND operations, but I can also do in an 8T cell, and since the read and the write part of the circuitries are isolated, then I can actually take in one cycle, I can read two word lines and then activate the write word line to be able to write into another set of cells. And that's what I'm showing, that it's possible to do that. And if you're able to do that, and again, the basic idea is that I'm really doing in-memory computing now, certain kinds of operations, and I've standard memory and an in-memory computing hardware. So the conventional instructions could be load, add, store, and I can potentially replace it by, for example, a computing memory add operation, as an example. Now, one can also do these kind of operations in a little bit different way by interleaving word lines and doing in-memory vector Boolean operations, where in this particular case, what I'm showing here is the same 8T cells, but I actually have, not 8T cells, 6T cells in this particular case, but I'm actually activating, I have two word lines per cell, and odd and even. So what I can now do is, if the odd word line is on, right, and they're connected to different cells, then I can store my data in such a way that I can actually do the operations. Each row has two read word lines, and the bit lines are connected to read and the compute blocks. These interlinked 6T cells with bit lines connected to the sense amplifiers now can do computation, and you don't have to do staggered activation, but you can actually now, because of interleaving, you're able to do these Boolean operations of NANDs and NORs, by activating two word lines, either the odd or the even, in two separate rows. Going further, one can certainly do multi-bit dot product operations. And this is, again, using 6T cells, it's possible to do it. Turns out, again, one can certainly have different kinds of inputs coming into the word lines, and your data is stored in your 8T cells like this. So what one can do is one can, again, now do summation of VI times WI, VI being basically the voltage which is shown on this particular word line connected to the read word line. Without going into the details of it, one can, if I just look at only the read part of the circuitry and connecting it to either, the input as an analog voltage to these M2, one can actually do and size your transistors properly to be able to do these matrix vector multiplication operations on these in these read bit lines. So the MSB is shown on the left. Of course, that would require a larger transistor because it's an MSB. A smaller transistor width it would do actually the next MSB and so on. And finally, the MSB is of length W. Now, this is a little bit complicated. Certainly, one can do a little bit better. And rather than, and this is basically reading currents, and each time you read a current, you need a transimpedance amplifier that can cost you. So rather than doing that, it's possible to also take these 80 cells and you pre-charge the bit lines. And by pre-charging the bit lines and having the read word lines activated, so you pre-charge the bit lines as I'm showing in the bottom right here. Step 1, pre-charge the bit lines to VDD, and then you have these read word line activation, which is a step 2. And based on what is stored data in your 60 cells, now we can do matrix vector multiplication, and you can read basically the voltage out of these bit lines now, and by that you can get rid of these transimpedance amplifier, which can be more costly. And again, one can show that the results show actually reasonably good accuracy by doing these computations. Now, few things. When you do such computations, you have these memory cores and so on. Then, as I mentioned earlier, it's possible to have a few things. It's possible to have ADCs, and these ADCs which are programmable. And as I mentioned, ADC programmability is important because of sparsity, and you can reduce energy consumption with these ADCs. So you can take these cores and build different macros with these programmable ADCs now. And what I quickly want to show is the results that with this programmable ADC and compared to a full-fledged ADC that you can potentially have, you can actually, in an architecture like Puma, you can actually get about 2.2x improvement in inference energy. And that's really coming only from the programmable ADCs. Going a little bit further, one can also do spiking neural networks, and the spiking neural networks I just want to mention is a little bit different from the standard neural networks. There's something, you have inputs coming in terms of spikes, and the membrane potential of these devices can be quite interesting. You can have a leaky integrated fire, or an integrated fire kind of neuron. And so every time, so when you have to get data, if you're storing things in the memory in a spiking network, in addition to the weight, you have to also get fetch data for the membrane potential, and that can be expensive. So to that effect, one can fuse and again do in-memory computing. If you can fuse the the weight memory and the VMEM memory together into an in-memory computing framework, and again, without going into the details of it, we actually used a 10T cell to do such computations, and it turns out one can actually have these computing macros in that particular case to be able to do not only ANNs, but also effectively doing spiking neural networks. Again, without going into the details of the design, it's possible to actually demonstrate different kinds of applications, like in this particular case, showing sentiment analysis and so on, using the intrinsic dynamics of SNN, but also doing in-memory weight and VMEM computations. Finally, let me look at the time. I guess I'm going to take a few more minutes, mention the fact, since I also talked about ROM embedding of RAM. I'm showing actually an example of a RRAM or an STT-MRAM RAM cell. But in this particular case, rather than having one bit line, I'm basically showing 2 bit lines connected to the cells. So either they're connected to the red line or to the blue line, the cells are. And based on where they're connected to, the blue line or the red line, you actually have a ROM value which is stored. How about the RAM? The RAM is stored, certainly in this particular case, I'm showing an STT-MRAM in the STT-MRAM itself. So to that effect, if I have to do regular RAM operation, I turn on the word line and I activate both the blue and the red bit lines. And then what happens is I end up doing the standard RAM read operations that I normally do. However, if I were to do ROM operations and I read the ROM, I turn on the word line and I activate one of the lines, not both. Let's say I activate the ROM, the red line. So in that case, obviously, anything which is connected to the red line, I'm going to read that resistance. In this particular case, anti-parallel or parallel resistance. But if nothing is connected to that line, I'm going to read actually an infinite resistance, right? So to that effect, having a right sense amplifier now can read the ROM data. So again, no extra cost. You can do read and write simultaneously. This is something interesting. You can store basically transcendental functions. You can store, for example, your different kinds of activation functions, sigmoid, stand hyperbolic, or in fact even leaky integrate and fire operations and so on. Finally, I'm going to end by just briefly talking about the fact that it's possible, actually, so far we talked about computations in the main memory itself, or rather the cache memory itself. Is it possible to do computing in the DRAM? To that effect, turns out, we looked at the possibilities of doing computation in the DRAMs. And here's an example of what one can do. Let's say that I'm going to do addition. And addition would require computing two majority functions for cout and the sum. And so what one can do then, it's possible that you have basically a DRAM, and the blue part of it basically is a standard DRAM array where you store data vectors in column-based fashion. That's important. You don't store the data in column-based fashion. So for example, these are the different vectors, A0, A1, and so on, B0, B1, and so on in blue. And then you potentially have the sum values, which can be stored here. You actually reserve a few extra rows, which are shown in red. And these are the only extra reserved rows which are shown for computing that we do. These rows basically would add less than 1% overhead. The results of A plus B is stored in the same column. It's possible to do massively parallel vector operations and no need for carry shifts across bit lines. So how do I do the majority operations? These are my sort of, if I were to really have these, think about this, the red cells that I showed, if you copy the values into those red cells from the blue cells, and let's say that you have some values which are stored there in your capacitor, by activating the word lines, you actually end up changing the sense, the value on the bit line, the pre-charge value on the bit lines by either plus delta V or minus delta V. And depending on whether it's a plus delta V or minus delta V, you basically say the majority function. In other words, you can get the sum. Going further, you can also do similar majority operation for cout. And again, I'm not going to the details of it. One can show that you can go in one time step, you can get both cout and cout1. And if I do that, and if I do now the computations, the first thing that I do is I take these bottom compute rows, I copy basically the A's and the B's. And after copying the A's and the B's, I do the computations that I showed, the majority computation that I showed earlier. And after that, I actually end up storing basically the sum in this location as I showed. Now, certainly if you do that, turns out you can do various kinds of operations. And this is basically showing that, I'm basically doing k nearest neighbor operation, acceleration. You have a host processor, main memory and DRAM, and doing in-memory DRAM computing. So in this particular case, the Manhattan distance computation is done in the DRAM, and the host processor does the sorting. And if I do that, and again, and compared to the baseline implementation in a generic processor, it turns out I can potentially get in this new system almost about 11.7x improvement in performance. Now you might say that, hey, you're only doing computations which are additions. Is it possible to do multiplications? And to that effect, one can also add, for example, an AND primitive inside the DRAM. And again, without going into the details of it, with a few cells. Again, note that only a few cells need to be changed at the bottom, and that doesn't add up anything to the area of the standard DRAM core. This is basically some changes to the cell with some extra transistors added for only a couple of rows, and which basically what one can do is by enabling this extra line that we have, which is called the AND word line, and by properly enabling the sense amplifier, you end up doing AND operations. Now, why AND operation is important? Because what now one can do is, since we did add operations, now by doing AND operations, I can actually do multiplication operations. So this is basically showing that AND and the add operations added together now, I'm able to do these multiplication operations in the DRAM array. I have these compute rows, and which are shown there, which are very few compute rows. The main array doesn't need to be changed at all, and you're able to do these multiplications on these reserve rules. Again, results. You can have special function units. You need the subarrays. So you have special function units consisting of ReLU, pooling, batch normalization, and quantized units, which are shown on the left. And the multiplication operation happens in parallel across the DRAM subarrays for data in the transpose layout. Now, very important to note is the fact that all the computations in this particular case and the memories are in the DRAM itself. And based on different levels of parallelism, it's possible to actually get a good amount of improvement in latency compared to, for example, a GPU, which is shown there for ResNet 18 on CFAR 100 and AlexNet on CFAR 10. Now, I probably have taken a little bit extra time. So here are my parting thoughts. While the possibilities of achieving large improvements in inference latency and energy is possible using in-memory computing scenarios that I talked about, there's certainly several challenges. And what are the challenges? What's the area efficiency of your memory? The area efficiency is important because how many word lines I can simultaneously turn on, and a good amount of area is now going to be taken up by my analog to digital converters. So low complexity, programmable, and in fact, in some cases for edge applications, getting rid of the A to D converter turns out to be quite interesting and important. Crossbar non-idealities, they do play a role. So device nonlinearity, access transistor, selected device, circuit level non-idealities, and process variability. Those are all very, very important. And in fact, the right power consumption in some of these non-volatile technologies turns out to be quite important if you're to really think about an architecture that can do training. And then that brings us to reliability and endurance of some of these non-volatile devices. And as I mentioned earlier, high write costs. I already talked about the A to D and the D to A converters. Also, we still have to think about the data movements, even in an architecture like what we talked about in an in-memory computing architecture. To reduce that is certainly going to be important, and again, for a lot of these edge applications and so on. Training and mapping into this hardware, there could be degradation over time in this non-volatile technology. And then certainly the things that I talked about today, we can certainly have vector operations. That's not a problem, but the floating point operations is certainly a problem using these kind of technologies that I talked about. And finally, there's a good amount of time I spend on SRAMs, but also keep in mind that the SRAMs would take up a good amount of area for doing in-memory computing. So that certainly needs to be considered. So with that, I'm going to end here, and I'd like to acknowledge my students who really helped me in making this presentation. Okay, thank you very much. I can try to answer any questions that you might have.
Excellent. Thank you very much, Kaushik. Let me stop the recording, and then we continue with the discussion.